Hello, guys. Welcome to another interesting session of my project ideas. Today, we are going to work and learn on a very interesting topic called big O notation. In the previous lectures, I told you about the time complexities and the various ways in which you can know about the time complexity of a program. We read about three different notations. One is big O, omega, and one was theta. I hope you all are with me till now. You all have already learned about all those things. You already follow my lecture slides. So if you have not read, if you did not understand the previous lectures, I'll recommend you please go to the previous lectures, watch it, and stuff will be very clear to you. After knowing about those lectures, after knowing about the basics, if you come here, you can understand better. Okay. So assuming you all know about what are asymptotic notations, now we move to the big O notation. Okay. So for a problem of size n, a constant time function is order of 1. So if you have a problem of input size n, your constant time function will be of order 1 or big O of 1. If you have a linear time function, the order will be big O of n. And if you have a quadratic time function, the order will be big O of n square. Mathematically, if you want to represent it, let's say we have g and f to be functions from this set of natural numbers to itself. The function f will be set to be big O of g if there will be a constant c which will be greater than 0 and a natural number n naught such that f of n will be less than equal to c of g of n, c into g of n for all n will greater than equal to n naught. This is basically the formula for the upper bound. The big O asymptotic notation will give you the upper bound as you already learned about in the last lectures, and mathematically you can represent it as fn is equal to big O of g of n, and there should exist a positive integer n naught and a positive constant c such that the following condition is satisfied, that is f of n is less than equal to c of g of n for all l is greater than equal to n naught. Okay, so what is a stepwise procedure for big O runtime? Figure out what the input is and what n represents. You have to figure out the input, and what the number of what n represents. What does n stand for? N basically stands for a number, as we have already read about that when we write big O of n, so it's basically the size. Then we express the maximum number of operations the algorithm performs in terms of n, because we are finding out the upper bound. Then we will eliminate all excluding the higher order terms. This also I showed you in the last lecture slide. If a function, the time complexity is represented as suppose n cube plus n square plus 1000. So you eradicate all the lower order terms and you take the higher order term, that is the time complexity will be big O of n cube. Then you remove all the constant factors as well. This is how you mathematically write for a big O notation. What are the properties? The properties are mentioned here. Let's have a look. Constant multiplication. If you are multiplying a constant to a function, so big f of n is equal to c into g of n, then big O of f of n will be equal to big O of g of n, because we eventually eradicate the constants. We always take the function, the higher order function. In case of polynomial function, suppose your polynomial terms, expanded polynomial terms are written as a0 plus a1n plus a2n square plus up to am into n to the power m. So big O of f of n will be equal to big O of n to the power m, because the last higher order term is n to the power m. Summation works as such. You have to take the max of all, because this is the upper bound. And in logarithmic, if suppose some certain function is log n of log n to the base a and g of n is log n to the base b, so these two are also equal because these two are constants and they basically we eradicate the constants. The asymptotic notation is basically used to measure and compare the worst case scenarios of algorithms theoretically. So big O always measures the worst case time complexity. So that's why it is the upper bound and it is most commonly used. For any algorithm, the big O analysis should be straightforward as long as we correctly identify the operations that are dependent on n, the input size. Next, runtime analysis. So when we are studying the general cases, we always measure the worst case theoretical running time because it gives us a vivid idea of the performance analysis. The fastest possible running time for any algorithm is big O of 1. It's commonly referred to as constant running time. So any algorithm, if it reaches the extent of big O of 1, that is your best case time complexity. You cannot have a time complexity which is less than big O of 1 because this is constant. So in this case where the time complexity is big O of 1, the algorithm always takes the same amount of time to execute regardless the input size. So if you take a 10, the size of array 10 and a size of array 100, the time complexities will be same. But this is rarely achievable because if you achieve it, you are on the, like, you have made the best algorithm. In actual cases, an algorithm's running time always depends on n. This is the size of the input or the number of operations which is required for each input item. Okay. So now let's look at the best to worst performance, like the time complexities. Let's compare. So a logarithmic function that is big O of log n, that is the best time complexity because it takes less time, log n time. Linear is big O of n. Superlinear is big O of n log n. Polynomial is n to the power c. Exponential is c to the power n. And factorial is n factorial. So the best case time complexity is big O of log n. If you get a time complexity of log n, that means you have made a best algorithm. And if you are getting a time complexity of n factorial, then you need to optimize your algorithm because this is a worst performance. Got it? Next. This is the comparison in terms of big O of n, which I said you here. This part, this I have represented graphically so that you can memorize it. Sometimes these questions are asked in an interview. They will give you certain things like n factorial, c to the power n to the power c. They will tell you arrange in terms of increasing performance or decreasing performance, or which algorithm is the worst, which algorithm is the best, which is bad, which is fair. So you need to have a look at this. Okay. So it is very important in interview perspective because this shows how clear you are in your time complexity. Then, algorithmic analysis. Let's have a look. This is also an important part because it is also sometimes it is asked in interviews that what is the time complexity of binary search? It's log n. It's actually log n base 2, but it's log n. Okay. Linear algorithm is big O of n, that is linear search. Superlinear is big O of n log n, which is like heap sort, merge sort. Polynomial algorithm is n to the power c, which is bubble sort, selection sort, insertion sort, bucket sort, matrix multiplication. Exponential is Tower of Hanoi. So these are basically the examples of the time complexities. The factorial is your brute force search. Brute force is what? The normal, the initial one, which is not optimized algorithm for the traveling salesman problem. It's an important dynamic search problem, dynamic programming problem. Then memory footprint analysis of algorithms. So now we'll have a look at the memory footprint, the space complexity. You learned about the time complexity. Now let's have a look at the space complexity. That means how much space the algorithm, the program takes. Because the space is also, it's very limited. The resource of this space is also very limited. You cannot exhaust the space. For performance analysis of an algorithm, runtime measurement is not only a relevant metric, but also we need to consider the memory usage amount of the program because memory is also limited. You cannot take multiple memory space for some simple problem. That's not important. I mean, that's not optimized. That's not smart of you. This is referred to as memory footprint of the algorithm, which is known as space complexity. So space complexity depends on two aspects. Firstly, implementation of the program, which is responsible for the memory usage. So, and other one is input size or the amount of storage required for each item. So first it depends on the implementation of the program, then the input size of the, or the amount of storage required. So the algorithms with best to worst time complexity is mentioned here. Ideal algorithm that is big of one space complexity is linear search, binary search, bubble sort, insertion sort, selection sort. Logarithmic algorithm is big of log n, that is merge sort. Linear algorithm is quick sort, and sublinear is radix sort. Don't get frightened, don't get overwhelmed by looking at these names. All these sorting algorithms, searching algorithms, all the DPs, all the graphs, trees, what you are looking now, that will be covered in the later part of the course. So stay tuned because we are on the initial slide right now. Just be with me, understand what I'm telling, and make sure you practice more and more problems. Then you can master DSA. Next, space-time trade-off and efficiency. So basically, there is always a trade-off between optimal memory and runtime performance. So space efficiency and time efficiency both are ultimately very important to determine the efficiency of your algorithm. But these two always reach opposite ends, and there are certain conflicts that if the space efficiency is higher, time efficiency is lower. So they never reach a optimal part. So the more time efficiency you will have, the less space efficiency you will have. So it goes inversely proportional that way. Let's have a look at an example. The merge sort algorithm is very fast, but it requires a lot of space. But the bubble sort algorithm is slow, but it requires a minimum space. So you cannot have two of the best at one time, right? You can have one at one time. Next, let's code. Let's have a look at the code. Now, see, DSA is not only about theory, okay? It's about coding as well. So I have already written a code for you. See, we have a program to find the time complexity for a single loop. We have declared the variables. This is in Python, okay? And we have declared the size, and we have a loop running for n times and a loop running for m times, and we are going to print the values of a and b. So what does it happen? What happens in this program is you append the value of a by 5 and increment the value actually of a by 5 in each instance of the loop, and in this loop you increment the value of b by 10. Let's run. I hope you have already guessed the output. Let's run and see. See, it's 25 and 50. So if someone tells you to calculate the time complexity in terms of big O of n, what do you say? It's big O of n plus m. Simple. Now let's have a look at the time complexities and how does it happen. Okay, let me make it full screen. Okay, so output is 2550, which you got there. The first loop runs n time and the second loop runs m time. The calculation takes a linear time, that is big O of, actually not linear, it's constant. I'm sorry, it's constant, big O of 1 times. So by adding the time complexity, you get big O of n plus m plus 1, that is big O of n plus m. So the time complexity becomes big O of n plus m.